Any excess charge that is placed on a conductor will reside on the surface of the conductor, and Gauss's law will allow us to justify this claim. In this discussion, we are going to assume that the charges, namely the C electrons and the excess charge that we place on the conductor, are at rest. You could imagine that if you came along and placed a whole bunch of positive charges at one location on a conductor, initially those positive charges would repel each other, they would tend to move away from each other, but at some point they would find where they're going and then they would come to rest. So we really only care about the final location of all the charges in this discussion. The way we're going to claim this is that the electric field inside a conductor should be zero. How can we justify that? Well, within a metal, there are going to be lots of C electrons. If you take any substantial piece of metal, there will be Avogadro's number of particles within that metal. And therefore, you expect there will be Avogadro's number of C electrons within that metal. If there were an electric field inside the conductor, then the C electrons would feel a force because F equals QE. If the electrons feel a force, they are going to accelerate. And if that is the case, the charges are still moving around and we haven't found the final resting state of the charges in our conductor. So basically, we're not done yet. When the charges find their final location, they're done moving around. And if they're done moving around, they're no longer going to be accelerating. If they're no longer accelerating, that implies there is no force on the charges, which implies there will be no electric field at the locations of these charges. Once the charges on the conductor have finally decided where they're going to reside, the electric field inside the conductor is going to be zero. Now we could draw a Gaussian surface that is completely inside the conductor. So here's a Gaussian surface inside the conductor. And if the electric field is zero everywhere inside the Gaussian surface, then the electric flux through this Gaussian surface will be zero as well, because flux through a surface is EA cosine theta. But if E is zero, then phi will be zero. Now, let us, instead of drawing a Gaussian surface somewhere in the middle of a conductor, let's just draw a Gaussian surface immediately below the outer surface of this conductor, like was shown in this picture. If the electric field inside the conductor is zero, then the electric flux through the surface will also be zero. Remember, this Gaussian surface is still technically inside the conductor. And if the electric flux is zero through this Gaussian surface, that implies there is going to be no electric charge inside this Gaussian surface. So the net charge within this Gaussian surface is going to be zero. And therefore, the extra charges that we placed on the conductor must be outside the Gaussian surface, or in other words, on the very outer edge of the conductor. Here we have a thick but hollow metal shell with a point charge at the center of that shell. We want the shell to be made of metal because we want to be a conducting material. We're going to investigate Gauss's law for a few different possible Gaussian surfaces in this scenario. So as a first example, let's consider Gauss's law if we place a Gaussian surface around the point charge within the inner radius of this thick metal shell. In this case, we will have a scenario very similar to placing a point charge in vacuum surrounded by a Gaussian surface. We have a point charge, we have some non-zero amount of Q enclosed, so we will have some non-zero amount of electric flux passing through our Gaussian surface. This is not going to be a very interesting scenario to consider. A more interesting case is to consider what would happen if you have your Gaussian surface be entirely between the inner and outer radius of this thick metal shell. So we will have our Gaussian surface be contained entirely within the metal of the spherical shell. And at this point, pause the video and see if you could think of what would be the total flux through this Gaussian surface. The total flux through this Gaussian surface is going to be zero. What is our argument for that? Remember that we defined the flux through a surface is equal to E times A times cosine theta. Earlier, we said that the electric field inside a metal is going to be zero. So if the electric field inside the metal is zero, that implies there will be no electric field passing through that surface. And if there's no electric field passing through the surface, then that implies there will be no electric flux through the surface. And if there's no electric flux through the surface, that implies there must be zero net charge within that closed surface. So how might that be realized? Notice that we did not specify the actual radius of this Gaussian surface. Is this Gaussian surface near the middle of the shell? Is it just below the outer edge or just above the inner edge? We were ambiguous on that account. Also remember that there are C electrons, electrons that are free to flow between the positively charged ions that make up the metal. So we could say that this positive charge will attract some of those C electrons, and the C electrons will try to get close to that positive charge. So there will be some electrons that are attracted, and they will tend to congregate on the inner edge of this thick spherical shell. After I have enough electrons on the inner radius of this thick spherical shell, such that the total charge of all these electrons is equal to the charge of that positive particle, then everything will settle down, and now the net charge within my Gaussian surface is going to be zero. If I had some electrons move towards the inner part of this shell, I'm going to have a few extra positively charged ions, and those extra positively charged ions are all going to be on the outer surface of this thick spherical shell. Remember, everywhere where I place this Gaussian surface, there must be total zero electric flux through this Gaussian surface, because this Gaussian surface is entirely contained within the thick metal shell. So if the Gaussian surface is just barely below the outer shell, or just barely above the inner shell, or something in between, there still must be total zero electric charge within this Gaussian surface. As a final example for this setup, let's consider a Gaussian surface that is entirely encompassing this thick metal shell. So for this Gaussian surface, I would essentially be back at the original picture that I had. For every electron on the inner radius of this thick shell, I'll have a positively charged ion on the outer radius of this thick metal shell. So every electron will cancel with an ion, but I still have this leftover positive charge at the center of my thick metal shell. So again, just like in the first case, our closed Gaussian surface is encompassing some non-zero amount of electric charge, so there will be some non-zero amount of electric flux through this closed Gaussian surface accompanying the entire sphere. Now let's ask what would happen if, instead of placing this positive charge at the center of our thick metal sphere, what if we moved it off to the side? We now shifted our point charge away from the center of our thick metal shell. Just like in the previous setup, if we were to place a Gaussian surface entirely within the inner radius of the thick metal shell and surrounding the point charge, this scenario would be identical to having a point charge in vacuum that's surrounded by a Gaussian surface. So this is not a very interesting case to consider. What if we place our Gaussian surface entirely within the metal shell itself? So just like before, what if this is our Gaussian surface? Again, the electric field inside the metal is going to be zero. So the total flux through this Gaussian surface is going to be zero. However, because the positive charge is now closer to one side of the inner shell than the other, there will tend to be more electrons congregating on that one side. The electrons want to get close to this positive charge. So I will have a few more electrons around here and a few fewer over here. At this point, pause the video and ask yourself, how do you expect the excess positive charge on the outer surface of this metal shell to distribute itself? Do you expect the excess positive charge to be congregated more on one side compared to another? Do you expect the excess positive charge to be evenly distributed or something else entirely? The excess positive charge on the outer surface of this metal shell will be evenly distributed over the entire metal shell. So we will have a scenario that looks something like this, where all the positive charge is just evenly spread out. Why does this make sense? Well, remember that charged particles have no memory of where they are or where they're going. They could see an electric field at their location, but that's all they could do. They can't see anything else. So if I were to compare a scenario where I have a hollow metal shell with a positive charge at the center, and then you have some negative charge in the inner radius of that shell and some excess positive charge evenly distributed over the outer radius of that shell. Or if I have a solid metal sphere that just has some extra positive charge placed on it, that metal charge would evenly distribute itself. Or if I have a scenario more like this. In each of these three scenarios, the electric field below the outer surface of the shell is going to be zero. The positive charges on the surface of the shell don't have any way to know what is beyond their immediate location. So they don't know if this is the case, or this is the case, or this is the case. So therefore, the way that the positive charges on the outer surface arrange themselves need to be the same for each scenario.